Welcome to the second video of this lecture series on operational amplifiers. In this video, we will be discussing some very important terms related to op-amp. The very first of them is input offset voltage. So what is input offset voltage? To understand that, consider this diagram of op-amp. Both of its input terminals have been grounded. So ideally, we should get zero voltage at the output, right? But practically, there exists some amount of voltage at the output, which we call as output offset voltage, output offset voltage. So why do we get this offset voltage, even though we have not applied any input? The reason behind the existence of this offset voltage lies in the very first stage of op-amp. An op-amp is a three-stage amplifier. It has three stages. The very first stage is a differential amplifier. This is the circuit diagram of a differential amplifier. It consists of two identical transistors, Q1 and Q2. Ideally, both the transistors must have same characteristics, same properties, and there should not be any difference between them. But practically, a slight mismatch exists between the two transistors because it is not possible to manufacture two transistors with same characteristics and same properties. Definitely, there will be some differences and slight mismatch between the two transistors. This slight mismatch between the two transistors creates a potential difference which is amplified by the op-amp, and we get this offset voltage at the output. So, this offset voltage results due to the slight mismatch between the two transistors in the differential amplifier. We do not want this offset voltage because it creates error in the output. So, how can we remove it? We can remove it by applying an equal amount of voltage as that of offset voltage with opposite polarity between the two input terminals of the op-amp. Suppose the output offset voltage of the op-amp is 4 millivolt, then we must apply minus 4 millivolt to nullify this output offset voltage. So, the input voltage which nullifies this output offset voltage is called as input offset voltage. Or in other words, we can say that the voltage that must be applied between the two input terminals of the op-amp to obtain 0 volt at the output is called as input offset voltage. Let us now talk about input offset current and input bias current. Ideally, op-amps have infinite input impedance, so no current should flow into the op-amp. But practically, when these biasing voltages are applied, then some amount of current flows into the op-amp, which we call as input bias current. Let the current flowing into the non-inverting terminal of the op-amp is IB plus, and the current flowing into the inverting terminal of the op-amp is IB minus. So what actually are these biasing currents and where do they originate from? To answer these questions, let's look again at the circuit diagram of the differential amplifier. You must have studied BJT amplifiers in your earlier classes, and you must be aware of the fact that when transistors are used in amplifiers, then some amount of current is always present in their base and collector terminals even when no input is applied. These currents are also called as quiescent currents, and they are present because of these biasing voltages plus VCC and minus VCC. So the base terminal of these transistors Q1 and Q2 are nothing but the input terminals of this op-amp, and these base currents IB1 and IB2 are nothing but the input bias current IB plus and IB minus. Ideally, these two currents IB1 and IB2 must be same, but as I told you earlier, a slight mismatch exists between these two transistors and their base currents also differ slightly from each other. So, the input offset current is actually the difference between these two input bias current, and the input bias current is actually the average of these two current IB plus and IB minus. Let me write it down for you. So input offset current IOS is equal to IB plus minus IB minus, and input bias current IB is equal to IB plus IB minus divided by 2. So input offset current can be defined as the difference between input bias currents IB plus and IB minus, and input bias current can be defined as the average of two input bias currents IB plus and IB minus. Let's now move on to one of the most important specifications of the op-amp, which is common mode rejection ratio or CMRR. When same input or common input is applied to both the input terminals of the op-amp, then the op-amp is said to be in common mode configuration. For example, if 2 volt is applied at both the input terminals of the op-amp, then the op-amp is said to be in common mode configuration. Or if common input is applied to both the input terminals of the op-amp, then also the op-amp is said to be in common mode configuration, and the applied input voltage is called as VCM. So ideally in this configuration we should get 0 voltage at the output, right? Because we know that output of the op-amp is AD times V1 minus V2, where AD is the differential gain or open loop gain of the op-amp. In this case V1 and V2 are equal, so this term becomes 0. So we should get V output is equal to 0, right? But practically some amount of voltage is present at the output of the op-amp, which is called as common mode output voltage, and it is denoted by VOCM. The ratio of this common mode output voltage to the common mode input voltage is called as common mode gain. So ACM, the common mode gain, is equal to VOCM upon VCM. The value of common mode gain practically is less than 1, but ideally it should be equal to 0, or we can say that the value of this common mode output voltage should be equal to 0, because suppose the op-amp is operating in a region where some noise signals of frequency 50 to 60 Hz are present, then these signals will be common to both the input terminals of the op-amp, and we will get an unwanted voltage at the output, which will cause an error in the actual output of the op-amp. So ideally the value of this common mode output voltage should be equal to 0. So CMRR actually defines how well an op-amp suppresses this common mode input voltage, and mathematically we can define common mode rejection ratio as the ratio of differential gain AD to the common mode gain ACM. Let me write it down. CMRR is equal to AD upon ACM, where AD is the differential gain and ACM is the common mode gain. Let's now talk about the last term, which is slew rate. It is also very important from exam's point of view. So slew rate actually defines that how fast or how quickly the op-amp will respond to the applied input. For example, consider this diagram of a voltage follower. A voltage follower simply follows the applied input. If 2 volt is applied at the input, then at the output also we will get 2 volt. If 5 volt is applied at the input, then at the output also we will get 5 volt. In simple words, we can say that the output of the voltage follower is always equal to the applied input. Do not get confused with the circuit diagram. You just have to focus on the positive terminal of the op-amp, where a square pulse varying from 0 volt to 5 volt is applied. So at the output also we should get a square pulse varying from 0 volt to 5 volt. But practically we get a waveform something looking like this. Ideally the square pulse should take no time to reach from 0 volt to 5 volt, but practically it takes some time to reach its maximum value. So this time taken or the time delay, this time delay is defined by slew rate, and slew rate is expressed in volt per microsecond or volt per millisecond. For example, if the slew rate of the op-amp is 2 volt per microsecond, then this waveform will reach 2 volt in 1 microsecond. If this slew rate is increased from 2 volt per microsecond to 5 volt per microsecond, then this waveform will reach its maximum value only in 1 microsecond. So ideally, the slew rate of the op-amps should be infinite, or it should be as high as possible. Now, let's look at the reason behind the delay. Why do we get this delay? What is the reason behind the slew rate? So as I told you earlier, an op-amp is a 3-stage amplifier. It has 3 stages. So in the intermediate stage of the op-amp, an internal compensation capacitor is present. So the slew rate of the op-amp depends on how fast that internal compensation capacitor charges or discharges. So slew rate is defined as the maximum rate of change of output per unit time. Hope you liked the video and understood the concepts. If you have any doubt, any question, do let me know in the comment section. See you in the next video.